For the introduction and for the invitation. So, and I guess let me start by saying I've been really enjoying the talk so far. Looking forward to the rest of the week. And this will be a little interlude with two particle systems that I'll give you a crash course on. And the projects I'm going to tell you about. So the systems, these two models are pretty old, around the 80s, and they've recently, in the last 15 years, got a lot of attention. And actually in the last year, there's been kind of an explosion that's just started happening, including the resolution of an old conjecture that I'll share today. So let me jump in and tell you about the models. So I'm going to tell you about two models. I'm going to be ambitious in a 15-minute, 20-minute talk and tell you about two models simultaneously. And the reason is because they're really brother and sister. One of them is a relaxation that has been easier to study. The main one that we're really interested in is the first one, Stochastic Sandpile, or SSM for short. And the relaxation is activated random walkers. So the setting is think ZD. You can do it on a general graph, but let's just think ZD for today. Or maybe a large finite subset, a large box in ZD. The inputs are some parameters. So for the stochastic sandpile, it just has one parameter, which is a mass parameter, the average number of particles per site. Activated random walk has two inputs, a density, particle density mu, and a sleep rate. And I'll tell you about that in a second. I'm using different parameters for the two models, zeta for the sandpile and mu for activated random walk, just to distinguish. So I'll always use zeta for the sandpile. Okay, so what are the rules of this system? It has many identical particles that are going to perform simple random walks. So I start with some shift ergodic distribution of particles. Think Poisson zeta per site. I just initially drop independent Poisson many particles per site with average zeta. And then I'll declare sites active if they have at least two particles, inactive if they have one or zero particles. Active sites topple. So imagine these as sand grains. So if there are at least two, then at rate 1, so it's continuous time, the usual thing with the exponential clocks. If there are at least two particles at some site, then at rate 1, a pair of particles topples, meaning they each of those pair takes an independent random walk step. Okay, so for example, on Z, if you have two particles at some site, they could, when that site's clock rings, they could both go to the right, or one could go to the right, one to the left, or they could both go to the left. Okay, that's it for the stochastic sandpile. So the only time particles can move is when they're at least two co-located at some site. Activated random walk is going to sound similar, but in some sense it's easier to study. So with the stochastic sandpile, particles only topple in pairs when they're co-located. Activated random walkers, they're just kind of lazy random walkers that get reactivated when they hit each other. Okay, so the setup is the same. I have some shift ergodic distribution. Think again, Poisson or Bernoulli mu particles per site. The particles themselves I'll call active or sleepy. Active particles just do simple random walk, and they fall asleep at rate lambda. So simple random walk on say Z at rate 1. They fall asleep at rate lambda. When they fall asleep, they stop moving. They're not doing their simple random walk anymore, but they can be reactivated when some other particle comes to the site that they are sleeping at. And when that happens, then they continue performing their simple random walks. Okay, so it's like, you have these independent random walkers, but there's this geometric condition for when they are and reactivated, when they're allowed to move. They have to interact with each other. Okay, so jumping right ahead to the, okay, there's a phase transition here in the mass. So, the kind of behavior, the first simple behavior I want to think about, the first phenomenon that can happen here is either the system fixates or it doesn't. There's lots of particle activity, or most particles fall asleep and don't ever get reactivated. So I'll call that fixation. I'll say an instance of this process fixates if the odometer at the origin is finite. I'll say in more detail what I mean by odometer, but So what do I mean here? I just mean count how many times a pair of particles toppled at the origin. If that number is finite, if eventually no more particles topple from the origin, then I'll say the system fixates. And because of the underlying ergodicity, this will either happen at all sites or at no sites that it's finite. Okay, and these simple considerations, along with the monotonicity in the mass, if I increase the mass of the system, that should make there be more activity. This fixation should be less likely. You get this phase transition. There's a question though. You go ahead.
Right. This is specifically on Z, or are we doing this on?
Did I?
Sorry.
Yeah.
So
So it's
no,
just on
this
Z
holds
or?
in great generality.
Okay, great.
Yeah, ZD. Think ZD, but this holds in. Well, okay, so you're right. So some transitive graph, but whatever. Yeah, ZD.
Okay, thanks.
Yep. But okay, and I'm suppressing the dependence on D. This zeta C, this mu C will depend on D for sure.
Yeah.
At least a priori. So okay, so I have this critical density where I'm going to have fixation if the density is above it, and fixation if the density is below it. If there are very few particles, things will fixate. If there are very many particles, things will not fixate. And okay, for stochastic sandpile, it's just it's a number. For activated random walk, it's a density mu that depends on the sleep parameter lambda. And it's relatively easy, for example, to see that these are both less than at most one. If you have more than one particle per site on average, then there should be kind of always some co-located pair, and so you will see topplings. That's not too hard to see that these critical densities have to be at most one. But it's not even obvious right away, and this indeed is the long-standing conjecture that can you show that they're strictly less than one? And so that's a new result. It's still being written, but in progress, that indeed the critical density for the stochastic sandpile on Z, so that result is just on Z, is strictly less than one. I'm showing you the state of the art here. There's some history I'm leaving out, but okay, it's also at least a half. That's sort of an improvement of an old result. But somewhere between a half and one. And that result kind of goes through the activated random walk results kind of came first. And then we were able to see how to do it for the stochastic sandpile. So a lot more is known, or a lot more was known about activated random walk. So yeah, I don't want to go into these aren't, I don't want to talk too much about these results, just to say that we do know something about this critical density. It's at least this lambda over 1 plus lambda. So we know something about the relationship between the critical density and the lambda. And very recently, just like a couple weeks ago, there's a very nice paper that generalized some of these ideas that had previously only worked for Z or Z3 or higher, where the simple random walk is transient. They found a nice technique that works in Z2, Fourier and Gaudier on Z2, that the critical mu is strictly less than one if the sleep rate is small enough, right? So if you make the sleep rate really small, that means particles will stay awake. So that helps you show that the system's active. Sorry, am I saying that right? So yeah, so okay, yeah. So you can get that there's an active phase, of a non-fixation phase, if lambda is small enough and mu is a little bit less than one. But again, this is a short talk, so I don't want to go into any of the proof ideas, except to tell you what the general kind of mode that we work in is. And it's a bit different from these general Markov chain kind of frameworks we've seen. It's all combinatorial. And the key idea is the following. So we first change the way that I think about the randomness in the system. And it's a common idea of the site-wise or diachronous Fulton representation, where instead of thinking of the particles as being the carriers of the randomness, instead of asking a particle, where are you going to go next, I put the randomness into the environment. So I imagine there being stacks of instructions at each site of ZD. And the way I'm going to evolve the system is I'm just going to pick a site one at a time where there is a particle, and ask the particle to follow the instruction, the next unused instruction at that site. So it's like this field of particles is just following some instructions, some random environment of instructions. And the reason this is useful is the
Excuse me.
following.
In
Question?
the
Go
previous
ahead.
slide, so G is ZD.
Yeah, sorry. Okay. Good. Yeah, G is just ED. Yeah, there's quite a bit of work on other graphs. So sometimes I do this for general graphs, and indeed, what I'm going to tell you right now is not special to ZD. Okay, so what's the value of this site-wise representation? It has an abelian property. So okay, what I said with the site-wise representation doesn't immediately give you a way to evolve the system, because you have to choose which site do I have evaluate its instruction first, right? I have this whole infinite field of particles. I have to tell you, do the instruction at this site and then do the instruction at that site. I have to give you some ordering. And you might wonder, what if the ordering changes the evolution of the system? This abelian lemma says it doesn't matter. So if you have some finite configuration and I have any two sequences of legal instructions, I always have to, if I want to topple a certain site, there have to be at least two particles there, or have to be following the rules of the system. That's what legal means. But okay, as long as I have any two legal sequences of instructions that are reorderings of one another, they both yield a system that is fixated, then they yield the same final odometer. So the number of times that each site was toppled is the same. Okay, so maybe this doesn't seem like a very powerful thing, or kind of like, why do I care? Why don't I just kind of pick an arbitrary one? Well, this is really the power of all the techniques we have right now for those results I showed you rely on some version of this. What they do is they find a really clever way to use the instructions that lets you say something. So I choose this very carefully designed toppling procedure. I'm going to topple these guys first, and then I'm going to, right? So this is a completely deterministic statement, but right, just some sequences of instructions, not randomly generated or anything, but really the power of it is that I can look at the configuration, and then I can look at the configuration of particles and then choose a toppling sequence that helps me show something about it, show that it fixates, or show that it stays active. Okay, so I'm being very hand wavy here, but so you can see that there's some, right, this is what I mean by combinatorial. I'm really playing very explicitly with the dynamics, trying to come up with a toppling sequence that does what I want. And okay, yeah. So important consequence is that this odometer is well defined. I can just I can look at the total number of instructions that I need to fixate some finite set of particles. That's a well-defined thing. Good. So I just sampled a couple of lemmas, some theorems from those from some various papers, from two papers, with those results, just to give you a sense of what we're actually showing, what actually goes into proving the system does fixate or doesn't fixate. Because of the abelian lemma, that only applied to finite sets. It's really all statements about finite sets and getting some quantitative estimates on how many instructions do you need, how many topplings actually occur before everything is fixated. Right, for a finite set, even if you're in the supercritical phase, you still fixate as long as you have less than the volume many particles. So that phase transition in an infinite domain is going to be replaced by a phase transition in the number of topplings it takes. And that's what these two theorems are saying. So in the subcritical phase, low density, think low density or high sleep rate, less activity. In this case, I'm looking at the ring, so Z mod NZ. And this thing says for any lambda and mu small enough, there exists some constants so that the number of topplings, the probability that the number of topplings is like bigger than n log n squared is small. So this is saying the total number of topplings I need is at most like n log n, which is low. Okay, so in the subcritical regime, it doesn't take many topplings to fixate the system. Things fall asleep quickly without much interaction happening. What about the supercritical phase? So the corresponding thing, the setup's almost the same. now I'm on the two-dimensional torus. For any density, I can take the sleep rate arbitrarily small, such that the probability that the number of topplings I need is smaller than some exponential, even bigger, exponential in n squared, is small. So this is saying I need like super exponentially many topplings in this supercritical phase to fixate the system. And the volume of these things is like polynomials. This is a huge number of topplings. There's lots of activity going on. I'm really waiting for some tiny probability event that everything simultaneously is asleep. Okay, so this is the quantitative version of that phase transition that we had with the zeta c and the mu c. Yeah, and okay, so I said we really care about the SSM, the stochastic sandpile, but of course, I mean, these are hard models to understand, and we have lots of complicated questions about them. So I'll take any model that I can that's similar and that I can say something about. And just to end, I want to show you a variant, a way of running these dynamics that gives at least a nice picture and suggests some questions. So it's this driven dissipative version. Right? The infinite version, or on the torus or on the ring, those all had mass conservation. The total number of particles doesn't change. This is a version where the mass is not conserved. So what I do is I start with a configuration on a large box. I run the dynamics, but any particles that fall off the edge of the box, I kill them. I forget about them. And when everything's asleep, when the system fixates, I just drop a new particle at a random site and continue. So the mass is changing here, but what you see is, okay, so there's not going to be what's the thing that's going to correspond to the phase transition? It's this phenomenon called self-organized criticality. So we're going to see that the mass of the system converges to the critical mass. And so what you're going to see is, okay, so I've got this configuration of particles. Those are the little pink dots on a 60 by 60 box in Z2. And then what I'm going to plot is just the density of particles, the fraction of particles in the box, the total number of particles divided by the volume of the box. Okay, and what's going to happen is it's going to converge to some critical density. The deeper the color of the square, that means there are more particles at that site. Yeah, so I didn't say anything about it, but right at the end here, let me just say that there are lots of questions this suggests. Like, what is this configuration of particles we're seeing? Can you describe the stationary distribution at all? I have no idea. Nobody knows how to do that. What are the fluctuations of this graph around the critical density? So, okay, let me stop there and say thank you.
Okay, thanks a lot.
Any questions?
Is there any question? Marcos?
What's on the diagram?
The plot there on the left. So that's the density of particles. So the total number of particles divided by the volume of the box. So when the density is very low, I just keep dropping particles at random sites, and nothing falls off the edge, so the density goes up by 1 over n squared. But eventually, I drop a particle, and it causes a toppling that pushes some particles to the side, so it goes down, and so that's where you have this driving force to the critical density.
So your model is kind of, I think you were waking up things immediately, right? I mean, upon hitting the activated random walk was immediately awake, right?
Sorry, it was immediately.
So I understood your model. The waking up happens instantaneously, right?
Yeah. Mm-hmm.
So if you would delay that by a random amount, would this then still kind of part of your result be true?
If you delay the activation by a random amount, I mean, so okay, I originally described it in continuous time, but really I'm working in discrete time, right? I'm just kind of picking, especially in these finite systems, I can just pick one active site at a time uniformly and topple it. So I don't know. I'd have to think about that, but my guess would be it wouldn't make a difference.
Okay,
really.
Thanks.
Okay.
We have no time for the question, but I'm sure the speaker will be happy to discuss with interested people. Okay, so let us thanks.
Thanks again.
Thank you.